Hello, everyone. Thank you for your presence for this conference. I'm very grateful to be able to present to you this talk, and I hope that you are all well. It's my first time at Singapore, and I'm very happy to be here today. I'm going to talk to you about open telemetry for API monitoring. My name is Danielle Kayumbi. I have been a software engineer for 14 years, specialized in distributed architecture. I worked for many great companies such as Deezer, Manu Manu, Equino, and I recently joined Capgemini Group. So, let's begin. As you can see, there is currently a plane crash happening. A crash that can be terrifying or even fatal. We are often confronted with this kind of situation with our applications in production. This crash could have occurred due to several reasons, but today I'm going to discuss with you the two main reasons. The first one are the errors in the code base deployed in production, despite the checks in the CI/CD. Then we have attacks from hackers such as DDoS or data breaches exposed by insecure APIs. It can have serious consequences on businesses by shutting down their systems during a few hours or even more. One of the companies that suffered serious consequences was Amazon Web Service, the leader of cloud computing. In 2021, they were hit with a very long outage which took down popular websites. It impacted millions of people as they couldn't use their services. The incident affected the infrastructure in the East region, which made most of the Amazon services unavailable. For instance, EC2, DynamoDB, TimeStream, Athena, Glue, Chime, etc. The list is very long. This caused a serious impact, making it impossible to deliver packages, stream movies, play online video games, order in fast food restaurants, buy airline tickets, medical exams were delayed, and so were education exams. Also, your favorite tools and applications were unavailable. Okta, Slack, Udemy, Trello. Wow, the impact was gigantic, a big crash. It was a worldwide event, so it was all over the news. What is the reason behind this issue? The reason is because the IT team deployed a new automatic job to scale up some services hosted in the main network. However, it led to a huge volume of requests to the services. And of course, this led to even more retry calls that created congestion and took down all the infrastructure. Unfortunately, it made the network crash. Finally, the IT team resolved the issue. However, it took 9 long hours to fix. So, how can we prevent this kind of issue and discover it quickly? The problematic is to identify outages as soon as possible. Outages can come from errors, latency, bottlenecks, or third parties down. Then we have to send alerts to before the system goes down. This is even more relevant on distributed systems. Just a reminder, a distributed system is a system whose components are located on different networks. In a microservice architecture, the microservices are independent. They can have their own database and communicate through APIs. We have to be very careful because if a service is down, it can affect the whole system. Here you have an example of a service down. we can see that if nothing is done quickly, it can progressively affect the entire system. And this situation can be worse in complex architecture that handle more than 1,000 of services like Amazon microservices architecture with more than 1,000 of microservices. The dots here represent the microservices and the lines the interactions between them. We have also the example of Netflix architecture with more than 700 microservices. So it's therefore important to observe the whole system deeply in order to improve the system and anticipate outages. For this purpose, we generally monitor operations from time to time in order to improve services, among other things. However, nowadays, just monitoring systems is not enough, mainly because it's too deterministic. Indeed, monitoring is to focus on analyzing predefined data collected from individual systems. But now we need to analyze data continuously based on the combination of past experiences to detect bug or vulnerable attack vectors. We also need to understand the relationships between the components of a system, applications, microservices, servers, databases, and so on. For this purpose, observability is the key success. It will help to measure all the inputs and outputs across several applications, microservices, servers, and databases. Generally, we represent the monitoring as the tip of the iceberg, and the observability is the part below the waterline. However, they work together to offer robust insight into the health of a system. So, observability relies on telemetry data. Telemetry refers to data emitted from a system about its behavior. The data can be traces, metrics, and logs. Once we have these data defined, we need to generate, collect, manage, and export them by using a framework. The solution is the framework Open Telemetry. Open telemetry is a mechanism by which application code is instrumented to help make a system observable. It was accepted by Cloud Native Computing Foundation in 2019, and it comes from the merge of open tracing and open census. Open tracing, we have the distributed traces and metrics, and with open census, we collect and export the traces and the metrics. Now I would like to present to you the fundamentals of the framework. Distributed tracing is a fundamental of open telemetry. It tracks a single request through all of its journey from its source to its destination, unlike traditional tracing, which just follows a request through a single application domain. There are three main components in distributed tracing. We have log, span, and trace. Let's start with log. A log is a message emitted by a service or a component. Here you have an example of a log compliant with syslog formats. You have the emission date, the priority level, and the content of the message. Logs don't need to be associated with a particular user request or transaction. Unfortunately, logs aren't extremely useful for tracking code execution as they typically lack contextual information such as where they were called from. However, they become far more useful when they are included as part of a span. So, what is a span? A span represents a unit of work or operation. It tracks specific operation in the application code. Here you have an example of a span. You have the name, mandatory, the time-related data, and other metadata called attributes to provide information about the operation the span is tracking. I recommend to inject the spans in specific classes of your code base, such as controllers, like HTTP actions or consumers, sensitive services, repositories related to database, message broker, HTTP client, and so on. Here you have an example of a span injected in an API. This is an API to get the cart of a customer in a marketplace. We can see that uh, we can simply inject the span by using the Open Telemetry library, and we can simply inject the metadata. Here it's the customer ID. This is a code written in PHP, but the implementation is similar with other languages, so no worry. To make your code lighter, you can use annotation, and here you have an example of how you can use annotation. The library is available in all the languages, PHP, Java, Go, .NET, etc. So don't worry. Okay, we presented the logs, the spans, and then we have the distributed traces. A distributed trace records the paths taken by request through multi-service architectures like microservices, servers, databases, and so on. Basically, a trace is a collection of spans. Here you have a representation of a trace according to OpenTelemetry specification. The entry point is the parent span. A parent span can contain many children span. In a span, you can have logs and tags. A span can be a request to another microservice. And in this case, in the microservice, you will also have the span and the other children span with their logs and tags. And the whole Um, these wall spans constitute the trace. To illustrate that, let's take back our example of an API to get a customer card. In order to retrieve the card, we need to get the products associated, so the card service will request the product service. Here you have the illustration of a related trace. In entry point, you have the get card operation span. Then you have the request in the database to retrieve a card. And then we get the products by requesting the product service through an API. And in product service, you can see the request to the database, and we can also put in the cache the product retrieved. And between the two, we have a context, which is very important. The context propagation is important because it keeps the correlation between the signals, regardless of where they are generated. It is usually managed by the instrumented libraries, so it's transparent for you. You don't have to implement anything. And to avoid interoperability problems between vendor implementations, there is a specific specification from the W3C, especially for the trace context. You can see the recommendation in the website of W3C. Okay, here you have an example of a trace with the different spans in Datadog. You can see in the current span, you can see the logs, the tags, the attributes, and you can see the other spans with different color and the interaction, the start time, the end time, and the relationships between them. So this is a complete trace in a real life example. Okay. Now, I would like to present another fundamental of OpenTelemetry, which is the collector. The OpenTelemetry collector receives, processes, and exports the traces, the metrics, and logs to a wide variety of observability backends. Collectors can be deployed in different ways. It can be an agent running in each host machine, or it can be deployed as sidecar. The collectors generally rely on OpenTelemetry protocol, the specification to describe the encoding, transport, and delivery mechanism of telemetry data. Here you have an illustration of how this mechanism works. Here you have another example of a mapping of the services generated from telemetry data and APM, Application Performance Monitoring, is an example from Datadog. I really like this tool. I think it's a powerful tool and you can test it. Mm. And if you don't have Datadog, you can also try Grafana or ELK. It's the same mechanism. Okay. As soon as we define the base, we can create the dashboards. The monitoring will help to collect aggregates, analyze, and visualize data in real time. We can build monitoring dashboards by implementing the four golden signals framework. The first dashboard is the latency. Latency represents how long it takes to service a request over a given time. Generally, traffic represents how many user requests are being received over a given time. And here you have errors, application, infrastructure errors, or failure. And finally, the saturation, which represents how the resources are used that run on a service. And for as illustration, here you have an example of a four graphs on Datadog, my favorite tool, related to latency, traffic errors, and saturation. All of these rules and metrics don't come from anywhere. They have to be defined by the team. In order to measure the system, we will use the service level management. On the next slide, I will talk about SLO and SLI. Service level objective describes a measurable aspect of an API, such as performance, scalability, or availability. Then you have service level indicator represents a measurement of the services behavior. It's a metric associated to the service level objective. For instance, service level indicator can be associated to availability. How many requests could be handled, or how does it take to read or write data? Okay, so as we have a solution defined, let's take a look at the AWS outage resolution. You know, I presented the reason behind the outage, which came from a congestion in the infrastructure, in the main network. This congestion create the incidents well, which immediately impacted the availability of the system. So to solve the issue, the IT team used the telemetry data. It is written in their blog. By analyzing the logs, the telemetry data, they found out that the issue came from errors in internal DNS. As they noticed in their blog, to avoid that issue, they disabled the automatic job for a short time and they add a security in the network infrastructure to avoid congestion uh, in case of congestion. So, comprehensive observability helps the team to react quickly to outages. The following three main steps are essential to help your team. Firstly, you have the prevention, then the discovery to monitor and alert, and finally come the resolution based on your expertise. So, thank you for listening. I hope this will be useful for you to implement OpenTelemetry in your projects or to go further. So, if you have questions, feel free to contact me. I'm available on Twitter, LinkedIn, or by mail. Mhm. And so, thank you to API Days for this great opportunity. I wish you a good afternoon. I wish you a nice day, and I'm looking forward to see you. Bye. Thank you.